In our previous video, we took a look at how our elementary row operations affect the determinant. So what we're going to do is essentially build on that idea, and we're going to extend the set of properties that we have for the determinant. Right? Now, before we do, I want to utilize a couple of those properties that we already know that will give us some insight into how we can evaluate determinants without doing a lot of work. As long as we can recognize a certain pattern, for instance, we can tell immediately what the value of the determinant is, no matter how big that determinant is, right? So let's start with this particular property. And this one has to do, it's something that's very easy to see. And once you see it, you know what the answer is going to be. So if A has a row or column filled with zeros, right? So if you have an entire row or column filled with zeros, then the determinant of that matrix has to be equal to 0, right? So just to kind of give you an idea of why that is. So suppose I have an n by n matrix, and so I have my A11, A12, dot dot dot, A1n, and then A21, A22, dot dot, A2n, and let's say and then I have a row in the middle somewhere, fourth, fifth, sixth row, but let's say that row is filled with zeros, right? And then we go down to AN1, AN2, dot dot dot, ANN, right? Well, the thing is, if this is my A, because of the Laplace's theorem that says I can use my cofactor expansion using any row or column. And the whole idea about that theorem is that if you have a row or column that has a lot of zeros, right, that's the row or column you should use. So if I were to choose this row, and I'm just going to call it row I. So if I am going to use row I to do my cofactor expansion, well, if we write it down, this is what it's going to look like, right? In fact, let's write out our cofactor formula. Right? So the determinant of the matrix would be AI1 times CI1. And again, I'm just using this to represent the ith row. And then plus AI2 times CI2 all the way across until I get to this last entry in that ith row, which is AIN CIN. But the thing is, if all the entries in that row are 0, then it means all these coefficients of the C's, those A's are 0. So I end up with 0 plus 0 plus dot 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 0, and therefore the determinant is equal to 0, right? So really useful. Now, how often do you see this? Well, I mean, you might see it, right? But just look for a matrix. If you have an entire row or column, then its determinant has to be equal to 0, right? So that's like a glaring red flag. Just say, hey, look at me. My determinant has to be 0, right? Now, there are a few other less obvious reasons why the determinant has to be equal to 0. And what I'm going to do with this, in fact, a lot of the following properties, what I'm going to do is do it generally for the 2 by 2. Because again, we made the argument in the previous video. Because of how determinants are defined, eventually you can break any larger determinant down into a whole bunch of smaller 2 by 2 determinants. So if we have a good idea of what happens in a 2 by 2 determinant, then we can make this kind of leap, this connection. Now, in a formal math class, you would have to use something called mathematical induction to prove it rigorously. But we're going to take it from an intuitive standpoint and say if we can figure out a property for a 2 by 2 matrix, then we're going to extend that property to all n by n matrices. All right, so here's this other one. So if A has two identical rows or columns, right? So two identical rows or columns, it turns out that its determinant has to be 0 as well, right? So the determinant of A must be 0, all right? Well, let's see what that looks like in the 2 by 2 case, and then you'll see why it has to be, right? So again, for a lot of these, I'm going to give you like a mini proof just showing you why it's true for the 2 by 2, and then we will make the leap that it's true for the n by n. So here's kind of the 2 by 2 case. Well, what would it look like if the matrix has two identical rows? Well, it would be, for instance, in the 2 by 2 case, where you'd have A, B, and then you'd have A, B again, right? That's what it would look like for the matrix to have two identical rows. Well, if this is the case, let's use our formula for the determinant of a 2 by 2 matrix and see what happens. Well, if I multiply these two, I'll get AB. If I multiply these two, I'll get BA, right? But again, these are real numbers, so they're commutative under multiplication. So this difference here is equal to 0, right? So you could have a matrix that's not necessarily filled with 0, but if you have the same numbers in one row as in another row or column, then the determinant has to be equal to 0, right? And this property can be extended even further and say if one row, right? So if one row is a constant multiple of another row, then the determinant has to be 0 as well. So if one row is a multiple, meaning constant multiple of another row, then the determinant of that matrix must be 0, right? Well, what does that look like? Again, let's write it down in the 2 by 2 case and see what happens. So in the 2 by 2 case, it says that A is equal to, now it says, so if I choose, for instance, AB as my first row, then I would have to write down like a constant multiple of this row as my second row. Now what constant would I use? Well, if I want to prove a property in general, I can't use a specific number. So I'm just going to use any constant, let's call it K. So if I then write down the second row as K, A, K, B, right, where K is any real number, then the determinant of this matrix, now this particular one came about, we saw something similar to this when we did our constant times a row. But this is slightly different. What we're saying is that these two rows, right, are just multiples of each other. That's a little bit different than saying just multiplying one row by a constant, right? So don't, even though it looks very similar to what we did in a previous video, there's a slight difference in the sense that we're saying you just take one row And to produce a second row, just multiply that first row by any constant, right? Well, let's see what the determinant will be. So I'll have A times KB, and then minus B times KA. And again, we can see that these are the same. Because again, by the commutative property of real numbers, this product is exactly the same as this product. So again, the determinant must be 0, right? So these three are really helpful, right? Because sometimes, you might look at a matrix and you have like one row being exactly the same as the other, and it also works for columns because of the Laplace's cofactor expansion theorem. Or you might have one row being a constant multiple of another row. And in both of those cases, all you have to do is state what you observe and then say, therefore, the determinant has to be 0. So you don't have to do any expansion. You don't have to do any row operations. You're just using these facts to conclude what must be true, right? Okay, so those are some easy properties to look for. Now let's answer the question about what if we perform certain operations on a matrix and then compute the determinant? How is the determinant of the new matrix related to the determinant of the old matrix, right? So let's just kind of go through and list some of the operations that we know how to perform with matrices and see how the determinant is affected by those properties. And the first one, let's look at the transpose, right? Let's look at the transpose. And again, I will illustrate all of these using 2 by 2 matrices, but all of these properties will hold for n by n matrices, right? So let's write down the general 2 by 2 matrix. So A, B, C, D is one way to do that. So now I'm not saying that there's any particular pattern here, not like in the previous ones, right? There's no particular pattern here. All we're saying is that we can choose any 4 real numbers to form our matrix, right? Well, we know what the determinant is, right? So the determinant of A is AD minus BC. Let's take the transpose of this matrix, compute the determinant, and see what the relationship is between the determinant of A and the determinant of its transpose. So let's write down the transpose, and we know that operation where the first row becomes the first column and then the second row becomes the second column. Well, this is another 2 by 2 matrix. Let's compute its determinant. So the determinant of A transpose, let's see. Well, look at that. It's still AD and then minus CB, which is the same as BC. So what we've just observed is after the operation of transposition, so after transposing a matrix, the determinant of the transpose is the same as the determinant of the original, right? So this is essentially our little proof, right? It's very easy to establish these properties for the 2 by 2 case, and then we can extend them in a natural way to the n by n. So in general, right, the determinant of a matrix is going to be equal to the determinant of the transpose of the matrix. So taking the transpose does not affect the determinant at all. All right? So that's one operation. Another simple operation is scalar multiplication, which is different from multiplying a single row, right? So let's see what happens if we do scalar multiplication, right? So scalar multiplication. So again, we're going to take a general 2 by 2 matrix, multiply the entire matrix by a scalar, compute the determinant of the result, and then see how the former relates to the latter, right? Okay, so scalar multiplication. So we have our matrix, right? And I'm not going to keep stating that A, B, C, D are real numbers. We stated that earlier, but here's our matrix. And now let's take any constant and multiply this matrix. Well, Ka is K little a, Kb, Kc, Kd, right? Well, now let's take the determinant of this. So, and the thing to notice is, see, when you do a scalar multiplication, each row, right? Each row gets multiplied by the constant. So if you think about it, the property that we proved for multiplying a row by a certain constant, it means that the determinant gets multiplied by that constant. But now there are two rows that are multiplied. So what this means is, right, so let's do a little algebra and then we can see the relationship here. So if we take the determinant of the constant times a, we would have Ka times Kd, so Ka times Kd minus Kb times Kc, right? Well, let's kind of simplify this. So this first one here is K squared Ad minus K squared BC. And now I can factor out a K squared. And what we have is AD minus BC. So in the 2 by 2 case, look at what happens. If I scale an entire matrix by a constant, so if I do a constant times the entire matrix, the determinant of that new matrix is K squared times the determinant of the original matrix, right? So then this is K squared times the determinant of A. So in a way, when you look at it, what happens is you essentially factor out a constant out of one row, factor out the constant out of another row, and those two factors contribute to K squared, and then what you're left here is the determinant of the original. So the question is, what does this property look like if you have a 3 by 3 or a 4 by 4? So let me show you just kind of a slightly more general idea. So if we have, for instance, an n by n determinant, and each row, right, each row is multiplied by this constant. So it's going to look like this: K A1, K A1 2, and then dot 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 K times A1n, right? And then we're going to have K A21, K A22, dot 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 K A2n, and all the way down we're going to have K AN1, K AN2, dot 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 K ANN. And let's say we're computing that determinant. So again, what I have here is a constant times an n by n matrix, and then we're evaluating the determinant. But again, we know what happens every time if you multiply just a single row by a constant. This determinant is equal to K times, so in other words, if I factor out the constant out of the first row, I'll have a K out here. factor out the constant out of the second row, I'll have another k here. And then dot, 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 factor out the k out of the bottom row, I'll have a k. So I'll have a k factored out of each row, and there are n rows there. So this is n factors. And what am I left with? Well, it's going to multiply just the regular matrix. So it's A11 dot dot AN1. I'm sorry, 1n. Right, so we will have 1n and then A21 dot 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 A2n all the way down to AN1 dot 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 ANN. So what we have here is k times k times k. Again, one for each row. So we're going to end up with k to the nth power times the determinant of the original matrix, right? So let's actually state that now, right? So if A is an n by n matrix, and k is a constant, and let's just say it's not 0, right? Then the determinant of the constant times my matrix is that constant raised to whatever power the dimension is. So it's going to be k to the n times the determinant of the original matrix, right? And this is a little bit, not a little bit different, but it's really an extension of that previous property of what happens when we multiply just a single row. When you do scalar multiplication, you multiply every row. So then for each row, we would have an additional factor of k, which is why it ends up being k to the n. So it's really important that for this particular property, we need to know the dimension of the matrix in order to utilize this property. So we would have to know the determinant of the original. We would have to know the n, right? How many rows, how many columns does that original matrix have? And then finally, we would have to know what constant is being used. And then we can do this calculation to figure out the determinant of that constant times the original matrix. All right? So that one's good. Now, the other two properties, when you think of what other operations we've done with matrices, we've certainly done matrix multiplication, and we've done matrix inversion. So what I'm going to do is to say, suppose we have two matrices, like A and B, and we multiply them. How is the determinant of the product related to the determinant of the two original matrices? All right, so now we're going to turn our attention to matrix multiplication. All right, so matrix multiplication. And again, we're going to do it for the 2 by 2 case, right? And then make this kind of inductive leap, right? So, so we need two matrices now. So let A be equal to, now I need two generic 2 by 2 matrices, because again, we're trying to prove a property for all 2 by 2 matrices, so I can't write down two specific ones. So what I'm going to do is this. I'm going to say like A1, A2, A3, A4. These are going to be the entries in my first matrix. And then let B be equal to, let's write down the entries in the other one. So again, I'll just use little b's for the second matrix, right? So that's what we have. And the only requirement here is that the A's are real numbers and the B's are real numbers. All right? So we can write down the determinant of each of these, right? So we can write down the determinant of A, and that will be A1 times A4 minus A2 times A3, right? So we have that one. And then we can write down the determinant of B, and that is B1 times B4 minus B2 times B3. And since we're talking about multiplying, what I'm going to do is I'm going to multiply these two determinants, right? So in other words, I want to know if I find the determinants first and then multiply the determinants, how is it going to relate to if I then multiply the matrices first and then find the determinant of the product, right? So there's a bit of algebra to do here, right? So buckle up. But first, let's do kind of the easier one. So this implies that the determinant of A times the determinant of B, well, this is what it would be. It would look like A1, A4 minus A2, A3, that quantity times this other quantity, B1, B4 minus B2, B3. Now, if we FOIL this out, there's not much. This is what we're going to have. We're going to have this, the A1, A4 times B1, B4. So we're going to have A1, A4 times B1, B4. Then we're going to have the A1, A4 times a negative B2, B3. So it's going to be a minus A1, A4, B2, B3. And then let's take this now, again, continue foiling out. We're going to have a minus A2, A3, and then B1, B4. And then finally, the last terms multiplied. Now, both of them have a minus sign in front. So when I multiply, I'm going to get plus A2, A3, B2, B3. Right? Now, because of the different letters and the different subscripts, we don't have any like terms here, right? So this is what we have for the product of these two determinants. Now, this is where it's going to get a little messy. So we're going to change the order in which we do our operations. So we're going to multiply our two generic matrices and then compute the determinant of the product and see how it relates to this. All right, so let's do that. So let's do A times B. So again, we know how to multiply matrices, but now we have to do it in this general way. So B1, B2, B3, B4, right? Well, again, there's not much that we're going to, be able to do except write down the expression, because it's going to be A1 times B1 plus A2 times B3. And that's it. This is essentially our process for computing the product of two matrices, but since these aren't specific numbers, we have to keep it general, right? And then do the same thing with row 1, column 2. So we're going to have A1, B2 plus A2, B4. Again, not much we can do. Now, second row, first column, that's A3, B1 plus A4, B3. And then finally, second row, second column, A3, B2 plus A4, B4. All right? Now, here comes the really fun part. We are going to compute the determinant of this product, right? So let's see what the determinant of AB is. Okay, so we have to take this entry times this entry. So it's A1, B1 plus A2, B3 times this other one here, A3, B2 plus A4, B4, and then minus, now we have to multiply these two, right? So again, what we're doing is we're applying our definition. We're multiplying these two, but because they're binomials, we're going to have to FOIL things out, and then we're multiplying these two, right? and then we're going to take the difference. That's what we have to do to compute the determinant of a 2 by 2 matrix. So now for the ones in red, I have the quantity A1 B2 plus A2 B4 times A3 B1 plus A4 B3. Now let's foil it out. Now, when we finish foiling this out, we're going to have 8 terms, right? So let's make sure we have enough room here. So we have A1, B1, A3, B2. So that's this times this. Next up, we have A1, B1 times A4, B4. So A1, B1 times A4, B4. And then let's do the inner one here. So we'll have A2, B3 times A3, B2. And then finally from this one we have plus A2, B3 times A4, B4, right? And then, now all the other ones, when we FOIL this second product out, is going to be negative. So it might actually be useful to maybe put the negative terms down here, right? So so we're going to have a negative A1 B2 times A2 B1. So minus A1 B2 times A2 B1, and then minus, now let's take the first and the last, so we'll have minus A1 B2 and then A4 B3, and then minus, now the inner ones here, A2 B4 times A2 B1. Oh, actually that's B. This is A3. That's not a 2. That would mess things up, because that's a 3 from right here. Right, so then this is a 3. Right, and so we got A3 B1, and then the last term is minus, and then it's the last one here times the last one here. So A2 B4 times A4 B3. Now, if we look closely at this particular term, so I'm gonna circle this one. You know, look at the numbers, look at the subscripts. It's 1, 1, 3, 2, right? Notice we have, let's see, where is that one? So, B2. Okay, so there's one other thing I needed to change, because this is a 3, so this one needed to be a 3 as well. So this one is a 3. There we go. Because I had changed it here but not here, because we used this product as one of our, like when we FOILed out. So now if you look at this term, right below it you see the negative of it. There it is, the A1, there's the B2, there's the A3, and then there's the B1. So these two cancel out, right? So those are gone. The next one is, if you look at this term, A2, B3, A4, B4, right there, look right below it. It's the negative of that exact term. There is the A2, there is the A4, there is the B4, and then there is the B3. So these completely cancel out. So we're left with, let's write down what we have left. So here we have A1, B1, A4, B4, and then I'm going to write it like this. I'm going to write the one right below it. I'm going to write it as minus A1, B2, A4, B3, and then I'm going to write the other one that's right next to it, minus A2 B4 A3 B1, and then write the other positive term, the plus A2 B3 A3 B2. Now, what did we just show? Well, this expression here in green is identical to this expression here. These are exactly the same. We just have to make sure that all the factors are there. We have the A1, we have the A4, we have the B1, we have the B4. Then in this term we have the A1, here's the B2, here's the A4, here's the B3. In the other negative term we have A2, we have A3, we have B1, we have B4, and then in the last positive term we have our A2, there's our B3, there's our A3, and then here's our B2, right? So what we've shown is this. We've shown that if you take the determinant of the product, you get the product of the individual determinants. And this is arguably one of the most important properties of the determinant. So let's state it as our result. So kind of summarizing all this algebra that we just did, we've established this fact. And again, it doesn't work just for 2 by 2, it works for n by n. So if A and B are n by n matrices, then the determinant of the product, AB, is equal to the determinant of A times the determinant of B. So whether you multiply the matrices first, and that's assuming, again, and that's why we make the assumption that they're both n by n. So there could be both 2 by 2s, 3 by 3s, 4 by 4s, etc. But if you multiply them first and then compute the determinant of the product, you'll get the same answer as finding the determinant of each of them separately and then multiplying the determinants together, right? So the order in which, as far as multiplication is concerned, you can either multiply before computing the determinant or after computing the determinants and still get the same result, right? What is not true, this is not true for matrix addition. So again, and it's really easy to come up with counterexamples to that statement. So I'm just going to make a note here, right? In general, the determinant of A plus B is not equal to the determinant of A plus the determinant of B, right? So unfortunately, under matrix addition, the order does matter. If I add the matrices first and then compute the determinant, I will not, in general, get the same result as computing the determinants first and then adding them together. All right? So really big property here. The determinant of AB is equal to the determinant of A times the determinant of B. Now, after all of that, we have one other operation to think about that we've learned how to do with a matrix, right? The inverse. So there are two ways we could do it. We could redo a process similar to this, right? Because we know we have a formula for the 2 by 2 inverse. So we could find the determinant of the matrix and then find the determinant of its inverse and then compare them together. But this is where this particular property is helpful, right? So now let's look at matrix inversion. So in other words, when we take the inverse of a matrix and then compute the determinant, how is that related to the determinant of the original, right? So let's look at our inverse, right? Now, think about how the inverse is defined. So if A is invertible, right? Well, first of all, we know, going back to the 2 by 2 case, that the determinant can't be 0, that AD minus BC cannot be 0. So then we can say this. In fact, this is a double implication, right? The determinant of the matrix cannot be 0, right? So that's one thing. But the other thing too is that if the matrix is invertible, then we know A inverse exists. So let me write that down. That's another consequence. So A inverse exists. Well, we know what happens if we take a matrix and multiply its inverse, right? Then we're going to get the identity, right? So this implies that the A times A inverse is the n by n identity, right? That's how it's defined, and that this is the fact that we've used to solve certain matrix equations. Well, what if we took the determinant of both sides, right? What if we took, oh wait, I forgot here, not equal to 0. There we go. What if we took the determinant of both sides of this equation? So if I took the determinant of A times the its inverse, well, that would have to be equal to the determinant of the identity matrix, right? Well, the property that we just proved is that if you're finding the determinant of a product, in fact, let me scroll back up so it's still right there. There is this property. If I'm taking the determinant of AB, I can write that as the determinant of A times the determinant of B, right? So I'm going to use that property here and simplify the left-hand side. So this is equal to the determinant of A times the determinant of A inverse. Now let's ask ourselves, what is the determinant of the identity matrix? Remember, the identity matrix is that special diagonal matrix that has ones on the main diagonal. And since it is a diagonal matrix, I can find its determinant by multiplying the entries on that main diagonal. So what I would have is 1 times 1 times 1 times dot 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 1. And this would be, I'll write it out, but this would be n factors, right? And this is because the identity matrix is a triangular matrix. In fact, it's diagonal, right? So AIN is diagonal. And we have a property previously where we proved that the determinant of a triangular or diagonal matrix is simply the product of the elements on the main diagonal. So if I multiply all the ones together, I'm still going to have 1, right? So this is 1 to the n, which is 1. So this is telling me that if I have the product of the determinant of A times the determinant of A inverse, that has to be equal to 1. So then I know that this is not equal to 0 because of this property here. So I can divide both sides by the determinant of A. So the determinant of A inverse is equal to 1 over the determinant of the original, right? So we have this, right? And this is how the determinant of the inverse of the matrix is related to the determinant of the original. It's by the reciprocal, right? And this, again, is a very important property, right? So there are the properties that we need to establish, and we've done, I think, a lot of work in this video establishing these properties, lots of connections with things that we've done before, and that's what we need in a course like this, is to start connecting a lot of these ideas together. Now in the previous video, or I'm sorry, in the next video, what we will do is just look at a specific example where we go ahead and utilize some of these properties. So hop on over and I'll see you there.